Okay, our next speaker is Jesús Alberto Jaimes and Sebastian 14 again. Their talk will be a philosophical approach of the quantum theory and of atoms and molecules.
This theory, the quantum theory of atoms and molecules, is a novel theory of chemical structure. And this theory is based, has a rigorous mathematical structure that conforms with the laws and principles of quantum mechanics and offers a very good scenario to study the intertheoretical relations between chemistry and physics. I will talk about, it's a brief review of the begun of quantum mechanics. In 1926, Schrödinger postulated the wave function that contains all the information about a chemical system. And this wave function must fulfill the Schrödinger equation, this one, where the C is the wave function and the expression between brackets is the Hamiltonian operator associated to the energy of the system. And initially, Schrödinger wanted to give a physical meaning to the wave function, like a phi vibrations process in the atom. He thought that this idea is more plausible than to think in orbitals. However, later, he emphasized that the wave function shouldn't be used in the interpretation, directly in the interpretation of the physical phenomena, because it's a function in configurational space and not in real space. Instead, he advocates its use for the obtention of this quantity, with which he defines the electron density. And the electron density, he obtains the electron density by the integrating of this quantity over all the coordinates of the electron, but one, which he is kept fixed in the point R, where one wants to know the electron density, and then calculate the sum of this integral for the rest of the electrons. And it can be said that the begun of quantum chemistry is with the work of Hadley and London in 1927, wherein they applied the wave function to the study of the hydrogen molecule. And they demonstrated that the quantum mechanics could account for the covalent bonding. And in this work, Hadley and London expressed the wave function like a combination of atomic terms, where the electrons, the electronic coordinates are exchanged between the atoms, and this process was associated to a quantum mechanical resonance. And in 1928, London noted that the physical consequence of this resonance is the accumulation of electron density between the nuclei. This electron density maintains the nuclei bonded. And in the paper of 1928, London gave these contour diagrams of the electron density for the symmetric and antisymmetric solution of the hydrogen molecule. The symmetric is associated to the binding state of the molecule, and the antisymmetric to the anti-binding state. And sitting London, with the help of these figures, we can imagine how in complicated molecules, the atoms which form a valence, a chemical bond, are connected by such a bridge of phi density, that is the electron density. And then according to Vader is the developer of this theory. The physical manifestation of the matter in real space is represented by the spatial distribution of the electron density, and the magnetic properties of the matter is given by the current density that describes the electron density. And then the topology of the electron density encodes and reflects the concepts of atom, bond, structure, and structural stability. Therefore, a theory of atoms in molecules based on the electron density enables us to link the language of chemistry with that of physics. Well, the topology of the electron density is displayed by the gradient vector field, and the gradient vector field is generated by the trajectories of the gradient vector. A trajectory points in the direction of the maximum increase of the electron density. And, the trajectories in the vicinity of a given nucleus terminate at this nucleus. And, this figure shows is a relief map of the electron density distribution for the formaldehyde molecule, where the maxima of the distribution corresponds to the atoms in the molecule. In this, this peak corresponds to the oxygen, another one to the carbon, and the smaller peaks represent are associated to the hydrogens in the molecule. The dominant morphology of the topology of the electron density is given by the attractive force between the nuclei and the electrons. And this attractive force leads to a natural partition of the molecular space into a mononuclear regions that are, in this theory, these mononuclear regions are associated to the atoms in the molecule. And these mononuclear regions are bounded by zero flux surface. And this zero flux surface ensures that the electron density associated to each atom in the molecule remains unchanged over time. And this figure is shows the zero flux surfaces for the formaldehyde molecule. And the red point is the oxygen, the black point is the carbon, and the two white points represent the hydrogen atoms. And between two atoms, there is a zero flux surface that defines the basin of this atom. And we can say that in this theory, two atoms that are bonded share an interatomic surface, a zero flux surface. The topological features are associated to critical points where the gradient vector is zero. And each critical point is characterized by its rank and its signature. The rank is the non-zero curvatures of the critical point. That is the dimensions of the critical point. And the signature is the algebraic sum of the signs of these curvatures. And we have only 4 stable critical points. And the first one is a 3, -3 critical point, where all the curvatures are negative and the electron density is a maximum in the distribution, and this critical point is associated to nuclear positions. The second one is a 3, -1 critical point, where 2 curvatures are negative and the electron density in the plane formed by these directions is a maximum. And another one curvature is positive, and the electron density in this direction is a minimum. And this critical point is found between 2 chemically bonded nuclei. This critical point is a so-called bond path. That is the bridge of electron density. And the third one is a 3, +1 critical point, where the 2 curvatures are positive and the electron density in the plane formed by these directions is a minimum, and another curvature is negative and the electron density in this direction is a maximum. And this critical point is found inside a ring of bonded atoms. And the last one is a 3, +3 critical point, where all curvatures are positive and the electron density is a minimum. This critical point is found inside a cage of bonded atoms. With the help of these critical points, we can define the molecular structure. And this figure shows the relief map of the boron trifluoride, where the maxima correspond to the atoms in the molecule. Well, the central peak is the boron atom, and the three peaks around this central peak are the fluoride atoms. And in this figure is a map of the trajectories of the gradient vector, and each point is the position where are the nuclei, and the trajectories, the lines, are the trajectories of the gradient vector, and these trajectories terminate on each nucleus. And in this way, the atom is defined. And between two atoms, for example, fluor and boron, there is a surface of zero flux that are not crossed, well, is not crossed by the trajectories of the gradient vector. And in this same point, where is the zero flux surface, we find a bond critical point that is the so-called bond path, where is an accumulation of electron density that maintain the two atoms bonded. And this critical point in the relief map corresponds to a saddle point. And well, in this slide, I show the molecular graph of the benzene molecule and the ferrocene molecule. In the case of the benzene molecule, we have an hexagonal ring of carbon atoms represented by black spheres, and the hydrogen by gray spheres. And between two atoms, we find bond critical points represented by red spheres. And inside the ring, we find a yellow sphere that represents the ring critical point. And in the case of the ferrocene, this is the molecular graph, where the white sphere is the iron atom, represent the iron atom, and this cycle and these are the cyclopentadienyls bonded to the hydrogen, the iron atom. And well, this molecular graph can be depicted by two pentagonal pyramids in this way, where we find bond critical points in the edges of the pyramid, represented by red spheres, and in the faces of these pyramids, we find a ring critical point represented by yellow spheres, and inside of these pyramids, we find cage critical points represented by the green spheres. Well, in this context, Bader argues that the notion of chemical bond is insufficient to account for all interaction between atoms and molecules, reason for which he proposed the use of the notion of bond path. This bond path is the bridge of electron density that maintains two atoms bonded, and it will be a universal indicator of bonding interactions. And moreover, this property is a measurable quantity because it can be associated to a bond path operator in the form of a Dirac observable. Additionally, this theory recovers classical theories of chemistry by means of the Laplacian of electron density. The Laplacian indicates the regions where there is a charge concentration. When the Laplacian is negative, there will be a charge concentration, and when the Laplacian is positive, there will be a charge depletion. And well, in this case, I show the methane molecule, and this molecule, according to the valence shell electron pair repulsion theory, has a tetrahedron structure. And this structure is the same that show its corresponding Laplacian, the gray figure. And in the other side, the carbon monoxide behaves like a Lewis base because it has an electron pair on the carbon, and this electron pair can be donated. And this is illustrated in the corresponding Laplacian, the blue figure, where this log is the charge concentration on the carbon atom that can be donated. And with respect to the boron molecule, this molecule behaves like a Lewis acid because can accept an electron pair. And this fact is illustrated in its corresponding Laplacian, where we can observe that in the center of the molecule there is a charge depletion near to the boron atom. And well, under this reductionist approach, the Q-time offers a complete reduction of the chemistry to physics by means of the substitution of the language of chemistry for that of physics based on theorems and forces. And within the critical position that have emerged, I will briefly comment to. One is by Getema, who argues that the Q-time is sensitive to the language of chemistry because employs many concepts of chemistry in its own development. And in the other side, Alstrom argues that the monist approach of Q-time rejects a pluralistic view of chemistry whose main value lies in the ability to make predictions. And with respect to our research, we are addressing the relation between the Q-time and the quantum mechanics and between the Q-time and chemistry. And we want to know if the Q-time can be considered a theory as such, or if it is rather a model of molecular structure. And until this moment, we have not that the Q-time, this theory is more similar to the ontology, to the Bohmian ontology, because talks about the trajectories and the particles has definite positions, and the atoms in the molecule has a criteria of identity, are indistinguishable. Well, that's all. Thank you.
Questions, comments?
So I'm wondering a bit about the relation between this talk and the previous one, because this is a specific theory about molecular structure, but there are other approaches. And we, of course, all know that this original Schrödinger picture cannot be corrected. It's not tenable, because there's dissipation and the wave packets spread out. And these structures are not, I think, stable in the course of time. So what exactly is the status of this approach compared to the other one that we heard a moment ago?
Sorry, why do you say that this image cannot be stable?
Well, there was a discussion in the 20s about Schrödinger's proposal. Perhaps I misunderstood, but this is in principle the same approach as Schrödinger proposed in the 20s. Is that so? So the electron so psi square is the electron density.
Yes, the main problem.
But that was rejected in the 20s already.
The main problem in that time is that you can, if you say that the phi square is a kind of field or a kind of thing with substance that exists in the space, when you have atoms with many electrons or molecules with many atoms, you obtain a phi square function with 3n dimensions. It's the same problem that some people that thinks that Bohmian mechanics can be interpreted as a field in the space. You have to say something about these 3n dimensions, because we live in 3 dimensions. I think that this was the main reason.
No.
That is just saying the original interpretation of psi square as rho was abandoned by Schrödinger because he realized that when you are not in a bound state situation, when your potential allows for motion, then the density spreads and you cannot interpret as a real density. That was his question. I mean, I'm not... But they are considering bound states.
Only bound states. Okay. But the potential should be very specific, I think.
I didn't read about this problem, but here the idea is that if you interpret that there is a flux of probability, and you interpret that as a movement of some electrons or some kind of matter, these people find surfaces, closed surfaces that enclose a region in which the flux is zero. So they say if the flux is zero, then there is no electrons that cross this surface. So all the matter that is inside this region remain inside this region. So in this sense, they say, I don't care about the time evolution because I know that any electron can go out from this region, and any nucleus and any of nothing. So the main idea is that, but I will read about this problem. I don't know how they fix it.
We have 5 minutes left for questions, remarks, comments.
But maybe there was a misunderstanding. The problem that is pointing out is the fact that you cannot interpret literally the psi square as a density of charge. And you know very well that. Yes. But you were using, I think, you used the word density of charge, but at the end you went into sort of Bohm interpretation. So that really was, I understood it as a density of probability, and you have in mind a motion of charges guided by psi. That's what you did? Or you interpreted literally that rho as a density of charge and J literally as a density of
Can I say
current?
something that I think about? I think that these people, they are thinking in density of charge. They think that there is something that is charged, and it is not right from the viewpoint of standard quantum mechanics. So I think that what they will do is to explain how this can be interpreted correctly to give some sense to this work. Okay. We think, and they will do that, I will not, but the idea is that perhaps a Bohmian view is closer to the idea that quantum chemists have in their mind when they are thinking about molecules with a structure and electrons moving around and crossing or not certain surfaces. So first, they have to take this theory. In quantum chemistry, I think that they don't know that Bohmian mechanics exists, for instance, and they are thinking in trajectories anyway. So the first step is to make a criticism to the standard interpretation of this, not interpretation, the standard view that perhaps it's like Dennis says, it's not correct. Quantum chemists are very intuitive in this sense. And then try to endow the theory or the model with a kind of better, not only better, but better for chemists view. I don't know if
no, it's first Ruth and after you.
I'm not sure that you would really have to have a Bohmian sort of interpretation to make sense of, to be able to come up with an account of the model that they have that would be compatible with standard quantum mechanics. I mean, it just kind of, my first impression is that if you could define an observable corresponding to measuring whether an electron from one region could be found in another region or could be found outside the molecule, then the wave functions that they're calculating give you probability, they give you predictions for that sort of observable, so that if you say, well, I want to measure whether any of these electrons that are described as being in this region bounded by one of these zero flux boundaries could ever be found outside, then clearly it's predicted that they wouldn't. So I mean, I'm just sort of questioning whether you have to have a Bohmian picture in order to make some decent sense of this model. Where
this is what I said. They don't say that. They didn't say that. What I'm saying is not that Bohmian. What I'm saying is not that Bohmian is the only way that you can give this. I mean, mathematically, it's correct. I mean, what is the interpretation? Is it true that they recover atoms in the molecule? This is the point. So I'm not saying that this is the only way, the Bohmian mechanics is the only way to give sense of that. What I'm saying is that Bohmian mechanics is the way to give sense of that more or closer to the way in which
the realistic picture that physicists understand.
I didn't say that. I said that the way in which chemists think about atoms and molecules.
And close this theory with some physical theory, because when you study this theory for first time, the first reaction is say, this is not physics, because they suppose a lot of things. For example, they ignore completely the issue of indistinguishability, because they say, okay, there is no flux, but then the electron is there and does not come out. Decio maybe yesterday put the example of Priscilla, and it's exactly the same situation. You cannot assert that this electron is the same all the time. So to think this, you have to have classical notions, or at least the notion of a trajectory. So in this sense, we say that if you think this theory from the Bohmian mechanics, maybe you can, you are most predisposed to accept that. But yes, we studied with this work some months ago, so we don't have many advances. But another question that we discuss all the time is if this is a real physical reduction of chemistry, or is a new theory that doesn't take account and other things, as for example contextuality, since they only see the electron density. For him, this is the only relevant observable, so they doesn't care about the Heisenberg uncertainty, this kind of things.
The question is just, I mean, there's some literature on in the Bohmian framework on the quantum chemistry and physics chemistry transition. So Xavier Oriol's book, I mean, Nino, you will know this better than me. Oriol's book, and I know from Chip Sabins, who's a philosopher in San Diego, and etc. There are lots. So there is, you can jump on the train which is running.
Okay.
There are more Bohmian people in chemistry than in physics. Relation with
Then I will ask you the names.
Thank you very much.